So, we have been discussing about the wave propagation solution in one dimensional continuous media governed by the wave equation. So, our main motivation for studying this kind of problems is that we would like to understand transient motion, or when one dimensional structure interacts with a boundary or an inclusion, etc., or it goes and hits something. So, we have looked at examples, such examples in our previous lecture. Now, today what we are going to study is motivated by for example, a bouncing ball. So, when we drop a ball, we observe that it hits the floor, which is considered to be much more rigid than the ball itself, and it bounces back. So, I mean in the real world, of course, the process is quite complex because of internal dissipation, acoustic emission, etc. But let us bring out the crux of this problem. So, we would like to understand what happens when a one dimensional continuous system, let us consider a bar for example. So, when a bar goes and hits another an obstacle which has a certain impedance. It could be an infinite impedance if it is a wall, or it could be an finite impedance. So, what we are going to study today is the axial So, let me draw this figure. So, this is a bar this is a finite bar which is going to go and hit a semi infinite bar. So, in order to simplify the whole problem, we come to this very basic problem in which two bars are colliding. So, this is moving with an initial speed, let us say v, towards this stationary semi infinite bar, and what happens after this that we are going to look at. So, we are going to fix our coordinate system at this initial location. So, so we consider this uniform finite bar moving with the velocity v and hitting this stationary semi infinite bar, and we assume that all the motion is in the axial direction. So, at any location x, the field variable for this finite bar is represented So, the axial motion is represented by this field variable u x comma t. Now, the motion of the bar of this finite bar just before collision So, if I call this initial speed as v 0, now as soon as this collides, what happens is this face of the finite bar feels this this semi infinite bar or this obstacle, and this information starts propagating in this bar. So, there is a propagating wave in the negative x direction, which carries the information which tells this finite bar that it has this face has hit an obstacle. So, this wave which carries the information will represent this with by g x plus c t. So, this is the gross motion of the bar, and over and above this there is this wave which is propagating in the negative x direction as a result of the collision. Now, this wave goes and so let us consider this how this wave is being generated. So, we will assume that we will consider that this semi infinite bar has an impedance z. This z we will consider special cases, special values of z later on. So, the boundary condition that sets this wave into motion is given by, so this is the force condition at this end, so if the impedance is z, then z times the velocity of this face of the bar must be the force, and that force is being felt by this finite bar as negative of z times the velocity. So, if you substitute this expression of u in here, so this is what we are going to get, and from here we can solve so g prime c t is given by this expression. Now, to take care of the causality, we can write g prime z where this is the Heaviside step function. So, this is to take care of the causality of this process. So, therefore, this is the derivative of the wave that propagates in the negative x direction. So, one can write down actually the velocity of the bar at any point So, that is the velocity wave that propagates in the bar in the negative x direction. So, now this solution is valid till the time L over C. So, L is the length of this bar. So, L over C is the time taken by this negative travelling wave to reach this free end of the finite bar. So, let us see what happens at the free end. So, at the free end, of course, there is a force free condition. So, this is our finite bar. There was a wave propagating in the negative x direction, and once this wave reaches the free end of the bar, is going to reflect back in the bar. So, let us represent this reflected wave from the free end as f x minus c t. So, therefore, we can now represent the wave field in the finite bar by this expression. Now, at the left end of the bar, the boundary condition. So, at the left end, the boundary condition now, you see the coordinate system has been put here. So, this is a force free condition at x equal to minus of L. So, this is our condition, and once we substitute this expression in here, and simplify, we are going to obtain this expression in terms of g prime and f prime. Now, g prime is already known to us, and if you substitute that expression of g prime that we just now derived, and we can write this f prime z. So, let me make this substitution. So, let me define this small z as minus L minus C t. In that case, the argument of g, which is minus L plus C t, becomes minus z minus 2 L. So, now, since we want f prime x minus C t and we already have this expression of g prime, so this is the expression of f prime, which is the positive travelling wave after this wave reflects from the force free end of the bar. Now, so therefore, the velocity can now be written as and once we substitute these expressions, so that is the expression of the velocity after this first reflection from the left boundary of the finite bar. Now, therefore, let us now look at what happens at 2 L over C. So, which means this wave g reflects here and f is produced, and now this f has reached this end of the bar. So, what we are interested in looking at is the velocity at time 2 L over C. So, in this expression, so we have the velocity here. So, in this expression we put this condition of 2 L over C, and we can calculate and that turns out to be Now, E A or E can be written as, we know that E over rho is c square. So, E is rho c square. So, if you substitute this here and make some simplifications, so this is the velocity field in the bar. Now, let us analyze this expression. You see, when z is infinite, which means the semi infinite bar is actually a rigid wall. So, if z is infinite, so the impedance of this obstacle is infinite, which means it is like a wall, a rigid wall. In that case, the velocity field so if you take this limit, so which means that at all points of the bar the velocity is v naught. In other words, the bar rebounds back. So, it was coming with an initial velocity v naught and it hits a wall, and after time L over c, it rebounds back with the same velocity with which it came. So, this is the case when this is a rigid wall. Now, we can consider the case where z is finite. Now, there can again be three cases. The first case could be rho a c is greater than the impedance of the bar. So, which means the impedance of the bar is greater than the impedance of this wall or the obstacle with which it is colliding. In that case, you see this this ratio is positive, which means that now the bouncing is such that the velocity is still in the direction in which it was initially moving, because in that case u t is going to be positive. Which means after collision the bar is still going to move to the right. In the case where the impedance of the wall and the bar they match, in that case this bar, the finite bar, comes to a complete halt, complete rest. And the other case, when the impedance of this bar is less than the impedance of the wall, then this ratio is negative, which tells us that there will be a bounce back of this finite bar. So, now we most of the time, if the conditions are suitable, if the damping etcetera are minimal, then most we will observe this phenomena where the wall is much more rigid than the bar itself or the object that is incident. So, in that case it is going to rebound back. When in other cases where the impedance is less than the impedance of the wall, which is more likely to happen actually, then it is going to bounce back, but not at the incident velocity, it is going to lose that velocity. So, where is it going to lose the energy? So, it is going to lose the energy in this wall or the semi infinite bar as we have considered. So, because this impedance is now finite, so some part of this energy of this finite bar which is incident here is going to go into this wall or the obstacle. So, that is going to so some of part of the energy is going to be radiated into this obstacle. In this case where there is complete impedance matching, in that case this bar is going to come to a complete rest, and in this case it is going to go into the obstacle. So, even after a collision it is going to enter the obstacle, because the impedance is much less compared to the impedance of this bar. So, these are some of the interesting observations that we can have. So, here we also observe that collision, even though it seems instantaneous, it is not, as we can understand that this takes place after a time interval of 2 L over c, where c is the speed of axial waves in this finite bar. So, the wave, the disturbance wave must travel this length of the bar twice before the rebound can take place, if at all there is a rebound. Now, so this example can be used to understand the phenomenon of collision of objects. So, here again using the wave solution we have looked at this transient phenomenon. Now, let us next look at what happens in a traveling string. So, vibrations in a traveling string or a translating string. So, we have discussed this the traveling string problem before, and the traveling string occurs in a loom or in a rolling mill etcetera. So, we can approximately model a thread line, a traveling thread line as a traveling string. Now, we are going to look at the wave propagation in a traveling string, how the solution can be represented using these traveling wave solutions, and finally look at scattering of waves in a traveling string. So, let us consider this string which is traveling at a speed v. So, we have derived the equation of motion for a travelling string. Now, here I have shown boundaries, but we since we are going to consider an infinite travelling string, we are going to look at waves propagation in travelling strings and understand the solution in terms of this propagating waves. So, which means that even if I have a disturbance in a finite travelling string, we are going to look at transient solutions. That means, when this disturbance has not reached the boundary. So, initially we are going to look at solutions which do not interact with any boundary. Later on we will see what happens when there is a boundary and there is an interaction. So, to begin with, we do not have boundary conditions. So, if you consider an infinite travelling string, then we do not have boundary conditions. Now, let us look at this little transformation. Let me define xi, a new coordinate xi as equal to t, and another coordinate eta as x minus beta times t, where beta is a constant. Now, let us recast this equation in these coordinates xi eta So, here the field variable was w x comma t, our new field variable is w tilde xi eta, and to determine the equation governing this new field variable, we must replace our derivative operators del del t as del del xi del t is 1, so that is del del t. Similarly, del del x is nothing but del del eta. Now, when we replace these derivatives here, then and we make simplifications, this is what we obtain. Now, if you make a choice, if beta is taken as v, then the equation reduces to the wave equation, but now in these coordinates xi eta. Now, we already know that the solution of the wave equation can be written as and if you go back to the original coordinates. So, this implies that in the original coordinates so, this is the wave propagation solution or the D'Alembert solution for the travelling string. So, now you can see that there is a positive travelling wave whose speed is c plus v. So, there is a positive travelling wave with speed c plus v, and there is a negative travelling wave with speed c minus v in the string. Now, then let us look at the initial value problem. We have looked at this before. We have looked at this problem for the static string. Now, we can once again look at this solution at the solution of the initial value problem for the travelling string. So, we normally have a displacement, initial displacement distribution on the string, and a velocity distribution. Now, from using the solution, so which we have written out here, so when I use this solution here, and similarly from the velocity condition, so we have to solve these two equations for f and g in terms of w naught and v naught. So, this we have done before. We have to integrate this second equation with respect to space and then solve for f and g. And if you do that and make the simplifications as we have discussed in one of our previous lectures, the final solution can be easily obtained. So, this is our solution for the initial value problem. So, when we have initial displacement, so these are the contributions in the solution and the initial velocity contributes in this way. Suppose we let us take an example. Consider a traveling string which is given an impulse So, given an impulse at x equal to 0. Now, we have discussed this before. If you give an impulse, it sets a velocity condition on the string. So, it sets a velocity condition on the string at the point at which this impulse is given. So, let us consider the velocity distribution as v naught delta x. So, where delta is the Dirac delta function. So, if you use this in the solution, so here is our solution. So, what we obtain, so initial displacement is 0. So, w naught is 0. We have this initial velocity distribution, which is the Dirac delta function. So, this is obtained as, so integral of the Dirac delta function is the Heaviside step function. Now, this has to be calculated at these two limits. So, this is our solution. Now, let us look at this solution. What happens for, so for different for different conditions, so velocity conditions v, let us look at the evolution of this solution as time progresses. But you can see that, so this is a difference of two unit step functions, and as time progresses there is a gap at which this stepping takes place. So, let us look at this this figure, where I have considered three regimes. So, here the velocity of translation is less than the speed of propagation of transverse waves in the string. So, in that case, as time progresses, the wave fronts, they are propagating in the two directions, though on in the positive direction, which means the direction of the string travel, the speed of propagation of the front is higher than in the backward case, as we expect. Similarly, when v is equal to c, the backward front does not propagate at all, because its velocity is now 0, while this forward wave now propagates at 2 times the speed of transverse waves in the string. Now, if v is greater than c, then whole thing is convected, the whole disturbance is convected to the positive side. So, this front is also convected to in the positive x axis direction. So, in the case of this infinite string, if you tap the string at a certain point, if you hit it, then you expect to see this front spreading out in the string, depending on the speed of propagation compared to the speed of propagation of transverse waves in the string. So, these are the conditions. I mean, this is what you will observe in the case of an infinite string, but suppose now this wave or a disturbance in the string goes and interacts with a boundary. So, let us study this case of scattering from a boundary in the case of a travelling string. So, this is the string travelling at speed v . Now, we consider that there is this incident wave. So, this is a semi infinite string. We will consider semi infinite string, and there is a wave incident from minus infinity. It is a harmonic wave, a positive travelling wave incident at this boundary, and what we expect is that there will be a reflected wave once this hits the boundary. So, there is going to be a reflection. We are going to study how this reflection process takes place. So, what is the reflected wave? Now, as we have discussed just now, that the speed of a positive travelling wave is c plus v. On the other hand, the speed of a negative propagating wave is c minus v. So, these are the phase speeds in the positive and the negative directions. So, we expect that this since this phase speed is the ratio of the frequency is to the wave number. So, if for the incident wave it is c plus v, then we expect in general, let us assume that it is omega prime over k prime is c minus v. I mean, unlike in the case of a static string where they must be equal, but now since the speeds in the two directions are different, we have to be careful that these may be in general different. So, therefore, if the incident wave is if the incident wave is written out like this, then so this is k x minus omega t. So, omega I have replaced as c plus v into k. Now, the reflected wave can see that it can be represented like this. So, where I have replaced this omega prime t as c minus v k prime, and k prime has been taken out common. So, therefore, the total wave field in the string can be represented like this. Now, the boundary condition is given by the 0 displacement condition at x equal to 0. So, this implies now, this has to vanish, this sum has to vanish for all times. So, this can happen only when and so we obtain this interesting result that the wave number of the reflected wave gets modified upon reflection from this fixed boundary in the case of a travelling string. This is unlike the case of a stationary string. While there is this phase inversion in the of the reflected wave. So, there is a phase change of pi upon reflection, which is as usual. We have also seen this in the case of a static string, but this is what is very interesting. The wave number gets modified upon reflection. So, today we have looked at two examples. And we have studied these two examples using the wave propagation solution. First one was the reflection process, a collision of bars, by which we understood the reflection process. We can understand the reflection process of let us say a ball on a rigid floor or similar collisions. So, we have seen how there is a finite time of contact. In which actually the waves travel in this object while it is in contact with the wall or the floor. The second example was that of a travelling string. We have looked at the wave propagation solution in the case of a travelling string, and we have also looked at the solution of the initial value problem. And finally, we have looked at the scattering process in a travelling media, in a travelling string, and we have seen how the wave number can get transformed upon reflection, which is an unusual dynamical behavior. So, with that we conclude this lecture.